Okay. Assalamualaikum warahmatullahi wabarakatuh. I am Mohamad RAZILY, and this is my partner, Muhammad Izwan Shafiq bin RAZAK. So we will do our mini project presentation for parallel processing and assembly station simulation. So introduction, in modern manufacturing, efficiency is everything. However, as production lines become more complex and more parts unexpected, bottlenecks can easily slow down the entire system. To understand this better, our team consisting of myself and my partner conducted a new project for our computer-aided production management course at Unicare LMFI. We use Quest simulation software to analyze and compare a standard assembly line against a scale-up, more complex production scenario. Our main goal today is to show how adding complexity affects production output, where the system breakdowns, and how we can use data to optimize labor and machine workflows. System overview. So for our, we have two. One is mini project, which is the extended of the lab scenario 3, which is the baseline. So for mini project, we have part A, part B, and part D for the parts. And then for the assembly, we have one A part combined with one B part, and combined with one D part equals to a one C part. And then for the assembly time is about 150 seconds. And then for operators, we have 5, operator 1 to operator 5. And for lab scenario 3, we have only two parts, part A and part B. And for the assembly, we have one A part plus with one B part equals one C. And then for the assembly time is about 120 seconds. And we only have 4 operators. So the simulation duration time is about 9 hours, and the breaks is 60 minutes total. Software we will using is Quest. So the theoretical calculations. So as we know, to get production rate, it equals to 3,600 uh, divided by cycle time. So for the mini project, for machine A, we have about 80-second process time. For machine B, 85 seconds process time. And machine D is about 95 seconds process time. And for the assembly station, we have 150 plus 15 seconds for the process time. And then for the cycle time of machine A, we have 80. For machine B, we have 85. For machine D, 95. And for the assembly station, 165 cycle time. So the production rate per hour for machine A is about 45. For machine B is 42.35. For machine D is 37.89. And for the assembly station, we have 21.82, which is the bottleneck station. So bottleneck identification, 165 seconds, which is the longest cycle time. So for the assembly station constraint, the assembly machine, which is machine assembly 1, remains the primary bottleneck in both scenarios. In the mini project, the addition of part D and the increased assembly duration, 165 seconds, intensified the bottleneck effect, significantly limiting system total throughput compared to sub-processing machines.
Okay, so then I will continue about the simulation analysis. For the machine breakdown impact, our value for MTBF as exponential by 3000 seconds. For MTTR uniform 180 and until 300 seconds. For the total failures is 15 occurrences across system. For the lost time is assembly station breakdown cost until 0.58 hour of the productions. So this is our simulation for lab scenario 3. And then for this simulation video for mini project. Okay, so for the machine utilizing for the mini project, which is we can see here is only 64.5%, which is for the assembly station, the load is 64.5%. For the machine A is 11.4%. For machine D, 10.3%. For machine B is 7.4%, which is a low utilization of the machine A, B, and D, highlights server downstream, blockage at assembly. For the labor utilization analysis, operator for assembly is 58.7%, which is highest load operates the bottleneck station. For the operator 3, fetcher, which is 17.3%, travel 6.7 millimeter, which is a high ideal time, 88%. For the operator 2, which is part B, is 8.6%, most underload, potential for task reassignments. So for the theory and actual discrepancies, for the breakdowns, the theoretical model assume 100% availability, MTBF or MTTR in simulation significantly reduce the effective time. For the synchronization, A1 plus AB, 1B, sorry, 1A plus 1B plus 1D, requirement causes starvation gaps. If any part is late, the assembly station is stay idle. For the operator travel, theory ignores the time taken for the operator 3 to fetch parts from distant buffer, which is A2, B2, and D2. For the buffer blocking, mismatch arrival rates cause buffer congestion and the upstream machine stalling. For the conclusion, in this conclusion, the simulation demonstrates that increasing product complexity by adding a third component directly penalize system efficiency, causing a 10% drop in overall performance due to the server intensified bottleneck at the assembly station, while sub-processing machine set idle for the majority of the shift. The assembly line struggle with part synchronization, operator transit delays, and machine breakdowns, proving that the theoretical production targets cannot be met without accounting for this real-world disruption. Ultimately, the successful scale this manufacturing system, future automation must focus on adding parallel assembly capacity, cross-training underutilized operator to support the bottleneck, and organizing the floor layout to reduce material handling times. That's all from us. Thank you.